welcome to the first in a two-part set of tutorials on the beautiful topic of circles. Now in this first tutorial I'll be talking about geometry, some very important geometrical properties of circles, particularly involving triangles that are inscribed inside circles, and we'll look at a couple of examples that are pretty typical for the sort of exam questions that are asked at this level. Then in the second part of this set of tutorials on circles, I will look at the beauty of pi. We'll talk about the circumference and the area of a circle. We'll talk about what are called sectors, and also just briefly touch on polygons as well. So with that, what better way to start a tutorial on circles than to draw a circle? And the best way to draw a circle is to use a pair of compasses. So here we are. It's not often in life that one can use such a simple tool to such great effect, but really to draw the perfect geometrical figure with such a simple device is truly a great thing. So there's a circle. Let's imagine drawing what's called a tangent. Now a tangent to a circle is a line that just touches the circle at a single point. So that's a tangent to the circle. It touches the circle right about there. And so the first thing that I want to tell you about circles is that if you connect the point at which a tangent touches a circle to the center of the circle, you will have two lines that meet at right angles. So here's the tangent. It touches the circle at one point. Let's call it P. If I connect that point P to the origin, to the center of the circle, these two lines are perpendicular, and that's an important property to know. A second sort of related property is that if I draw any chord, and a chord is a line that just spans the circle from one point on the circumference to another, if I draw any chord and then I draw a line that cuts that chord exactly in half, now this you can see is a broken ruler, but let me just see if I can measure this. Oh, it's surprising, look, it's exactly 2 centimeters. So if I just indicate the halfway point and draw a line from the center of the circle through the halfway point of that chord, this splits the chord into two equal lengths, of course, but the property that you need to know is that these two lines are also at right angles to each other. Okay? And the exam questions that tend to be asked will touch on or essentially imply the knowledge of these kinds of properties. Now, these angles have to be right angles for reasons of symmetry, actually. There's no other angle they could be. There's nothing that breaks the symmetry between the left and the right side of this construction, same here, and so actually the angle has to be 90 degrees because the total angle of a line is 180 degrees, so this must halve that angle because of symmetry, and the same here. Another beautiful property of circles, which is less obvious, is the following. If I draw another circle, there we are, and there's the center, and I draw any chord through the center of the circle, that is what we call a diameter of the circle. And now I choose any point I wish on the circumference, and I make a triangle with the diameter as one side of the triangle and that point I chose on the circumference making the other two sides of the triangle. Then it is a property of this construction that this angle opposite to the diameter is a right angle. Let me just show you just randomly another point there. I just chose a point randomly on the circumference. I make a triangle using that point and the diameter as one side of the triangle, and this angle opposite to the diameter is a right angle. Now that's less obvious why that's true. There's not an obvious symmetry argument you can use, but here's a simple proof, and I'll just sketch the proof rather than go into details. But maybe if you're one of the hardcore mathematicians, you can fill in the gaps and convince yourself this is true. But I'll just show you how you can prove this. So let's draw a line between this point on the circumference and the center of the circle. And let's just label this angle here as A degrees and this angle here as B degrees. Then what you can see is that these angles A plus B must add to 180 degrees because they're just on a straight line. Okay? Now, when you're dealing with problems involving circles and triangles inside circles, it's very important to identify radii, which lengths of the triangles are actually also the radius of a circle. You see, this is a radius from the center of the circle to the circumference. This is a radius. This is a radius. And by doing that, you often identify isosceles triangles. So this is an isosceles triangle, and this is an isosceles triangle. Therefore, in this triangle, these two angles must be equal. And likewise, in this isosceles triangle, these two angles must be equal. And so I'm going to leave it there for those that are interested, but it's not really very difficult to take the fact that these two are isosceles triangles and the fact that angles A and B add up to 180 degrees to show that this angle here, which is the sum of the red angle and the black angle, must be 90 degrees. Quite a nice little proof, that. So that's three important properties of triangles that are purely geometrical. Let's just recap them quickly. A tangent to a circle is a line that just touches the circle at one point. The line that connects that point to the center of the circle is at right angles to the tangent. A line from the center of the circle outwards that bisects a chord meets that chord at a right angle. And both of those properties are purely down to symmetry. And then this third rather lovely property, which is that if you draw a diameter in a circle, a diameter is a chord that passes through the origin, then any triangle that you make using the diameter as a base, where the other two sides connect to a point on the circumference, then that angle opposite to the diameter is a right angle. And I just demonstrated it here with two different triangles and sort of hinted to you pretty strongly how you might construct a proof to show that that's true. So for the remainder of this tutorial, I just want to make up two problems that are very typical of the kind of exam problems that you get asked at this level of maths that invoke these properties. So let me draw a circle. Okay, and let's see, I want to draw a tangent. If I can, draw it fairly flat. So there's a tangent, and here's the line that connects the center of that circle to the point where the tangent touches the circle. And then I'm going to draw just an arbitrary line through the center of the circle. And I'm going to draw another point on the circle here. And I'm going to make some triangles. And these diagrams, when you see them in the exam papers, honestly, you look at them and you think, oh my goodness, I'll never be able to understand this. Okay, but actually, even though that's a very natural first reaction, they're not too difficult really, these problems, because you just have to identify, as we're going to see now, the properties to do with right angles and such. So let me label this crazy diagram. There's the center of the circle. There's the point, I'll call it P, where this tangent touches the circle. And let me just label these other points A, B, C, and D. And let's just say in this particular problem, they gave you this angle here, and they gave you this angle here. Let me just make up a value for that. Let's say that was 28 degrees. And let's say this angle here, I don't know, that looks like it's quite big. Let's say that was 63 degrees, okay? And so here would be a typical question. What is the value of this angle? Okay, so we have to find the angle of BAP, which is a sort of a British word for a roll, actually. Angle BAP is the question. So, terrifying at first, but actually not too bad. So, let's quickly identify the right angle, shall we? Well, first of all, we know that this is a right angle because this line connects the center of the circle to the point where this tangent meets the circle. So that's a right angle. And then we notice that this is a diameter, and we've got two different triangles that are drawn from that. So this must be a right angle, and this must be a right angle. So straight away, actually, having seen that this is a right angle triangle, we know that's 90. If we know this angle, we can immediately say that this angle here, so not BAP, but CAB, or back, is 90 minus 63, because this angle and this angle must add up to 90. So let's see, 90 minus 63 is 27 degrees. So we know that angle, that's not too bad. Now what else can we do? We can read off this angle pretty quickly because we have a right angle triangle, that's 28 degrees, so this angle here must be 90 minus 28, which would be 62 degrees, okay? And we can then actually read off this angle straight away because this is a straight line, so this total angle must be 180 degrees. So this angle must be 180 minus 62, which is 118 degrees. And finally, I think to finish this off, we just need to identify some radii. Well, here's the center of the circle. This is a radius, this is a radius, this is a radius. And you see we have all these isosceles triangles flying around. You know, you can finish off this problem any way you like, to be honest. Let's finish it off in style. Let's say this is an isosceles triangle. So this angle here and this angle here must be the same. And each of them can be gotten from taking this angle from 180, which we know is 118, and then they're each going to be half of that. So that's going to be 59 degrees if I'm not mistaken. And those two angles. So if you have an isosceles triangle and you know, well, actually one of the angles, you can get the other two. In this case, these two angles must sum to 180 minus 62, and because it's isosceles, they're equal. So we take 62 from 180 and we divide by 2, and that gives us each of these angles. And finally, in this big triangle here, this right angle triangle, we have a right angle here because there's a diameter as one of the sides. So this angle here must be 90 minus 59, okay, because this is a right angle, and 90 minus 59 is 31 degrees, and then we have enough to get BAP then, because BAP is the sum of this angle and this angle, so it's 27 degrees plus 31 degrees is 58 degrees. Okay, phew. These kinds of problems are like not not a wild goose chase, let's call it a goose chase. We're going to catch the goose because we actually know what we're doing. But you have to kind of follow your nose, because I didn't know, even though I set the problem, I didn't really know what the answer was or how we were going to get there. But I know that these are the kind of problems that get set. And you just have to follow your nose and use the obvious properties that are in front of you to do with right angles and isosceles triangles. Okay, that's not too bad. Let's just quickly check. We could have gotten this angle by noting that this is an isosceles triangle. We know that's 118. So these two are the same, and they must add up to 180 minus 118. So they must each be half of 62, 31. So that's just a little check there. Good. And to finish off the tutorial, let's just do another kind of problem that the examiners in Scotland in particular love, and you are guaranteed that you will have one of these problems on the exam every time. And it's the following. You have a circle, but what they do to the circle is they cut part of it off, okay? So here's my circle, and they cut part of it off. And then you're asked to find the height of this sort of cut-off circle, given some information about the base. So let's call, let's say the base, we're told, has a width. I'll just make up some numbers here. Let's say that we're told that that's 4. Okay, for the sake of argument, we're told this is a right angle, and we have to work out the height. And we're told that the radius of the circle is, let's just try and make this reasonable, the scale I've drawn it. Let's say the height is 3, the radius is 3. And our challenge then is to find the height. That's kind of an interesting sort of question. So h, what is the height? Now the way to do this is the following. You first notice that we have a few radii around. We can say that this is a radius and this is a radius, namely O2, let me call that T for top. So we can immediately read off this number is 3. So let me call this length here, let me call that A, okay? And so we know that the height is 3 plus A, and that sort of simplifies the problem down, because now we can just focus down here. And the reason I want to focus down here is because these problems where you have a cut-off circle always involve a sneaky application of Pythagoras' theorem. So you see, because I have a right angle there, if I draw the line from the origin or the center of the circle to where this base cuts the circle, I have a right angle triangle where I know the hypotenuse because it's yet another radius, and that is 3. And then, because we're told that this is a right angle, it's bisecting this base, and so this length here is 2, and we have a very cute little application of Pythagoras' theorem here. So the hypotenuse squared is equal to the square of 2 plus the square of A. So we have that 9 equals 4 plus A squared, namely that A squared is 9, take away 4 is 5, and so A is the square root of 5. So the height of that cut-off circle then will be 3 plus root 5, whatever the units might happen to be. Root 5 is a wonderful number, by the way, connected to something called the golden mean or the golden ratio, and I'll have to give a mini tutorial on that sometime, because that really is beautiful maths, beautiful, beautiful. Right, I'm done with this first tutorial. I hope that's been helpful. I hope these 2 examples were okay to follow. And in the next tutorial, we're going to look at pi. Talk about beautiful numbers. Root 5 is beautiful, but pi is the king of beautiful numbers, or the Queen, whichever way you like to describe your royalty. So we'll talk about pi and related concepts of circles. So I look forward to seeing you then.